In this video, we'll be checking out rotational kinematics. So what's important here is looking at objects and how they move around rotationally. So when an object moves from location A to location B, one of the things we need to know is how to measure its arc length. Its arc length is simply this distance from location A to location B. So we also need to review how to measure radians. So a radian is basically when you've got a triangle like this, and it's not really a triangle, but a section where you've got this radius and this arc length that are equal. Halfway around is pi radians, and all the way around is 2 pi radians. So what's really important to know is that it's 2 pi radians around a full circle. In this example, we're going to look at how angular velocity is measured. Angular velocity is measured by taking the angle and measuring it over time. And we call that angle the angle that's subtended. So every second, pi over 4 or 2 pi over 8 radians are subtended. So in the first second, 2 pi over 8, and then in 2 seconds, after 2 seconds, you'll notice it's 4 pi over 8, and so on. If we graph this, we notice a linear relationship between the angle in radians, the displacement, versus time. If we look at the slope and the vertical intercept, we can look at the physical meaning of the slope. The physical meaning of the slope in this case is what we call the angular or rotational velocity. We measure that, or we use lowercase omega as a symbol for that, and the units are radians per second. The physical meaning of the vertical intercept is the initial angular position. In this case, it's 0, and again, angle is measured in radians. So if we take our y equals mx plus b equation and observe this graph, we notice that in the vertical, our variable is theta, or the angular displacement. Our slope is 0.78 radians per second. Remember, the way we measure this slope is by taking the vertical units and dividing it by the horizontal units. So that's radians per second. Our horizontal variable is t for time, and again our vertical intercept is 0 radians. So this is the equation for the graph, and the general equation for this relationship is theta is equal to omega t plus theta initial. So when the angular velocity is constant, as in this picture, there is a linear relationship between the angular displacement and the time elapsed. In this example, the angular velocity is increasing over time, and we notice that the angular velocity and the angular displacement is occurring in the clockwise direction. So we would call that direction negative. That's the convention for rotational motion, the fact that counterclockwise is positive and clockwise is negative. If we make a graph of the rotational velocity over time, we find that we have, once again, a linear relationship. This is with the angular velocity, omega, versus time. If we were to measure or calculate these, the important features of this graph, we get a slope of negative 0.229 radians per second squared, and a vertical intercept of 0 radians per second. What's the physical meaning of the slope of this graph? The physical meaning is the angular or rotational acceleration. The symbol for that is alpha, and the units are radians per second squared. What's the physical meaning of the vertical intercept? That's the initial angular velocity, omega initial, in radians. And so if we were to write a y equals mx plus b equation for that, we get omega is equal to negative 0.229 radians per second squared times t plus 0 radians per second. And that gives us one of our rotational equations. So we find that when the angular acceleration is constant, as in this example, there is a linear relationship between the angular velocity and the time elapsed. Let's observe this black object as it goes around in a circle. Notice that we can draw a dot here for its angular velocity at the beginning and show the angular velocity as a pseudo-vector as it goes around the circle. We can also draw in the rotational acceleration as the object goes around the circle. That would be our version of the motion map for rotational kinematics. So if we were given the question to derive the value of the acceleration of the object if it starts from rest and attains an angular rotational velocity of 2.0 radians per second in 4 seconds, then what we would need is the rotational version of the kinematic equations. Notice that they're very similar to the linear kinematic equations. So we've already done our first step. We've drawn our pseudo-vectors. They're called pseudo-vectors because they're not real vectors. And then we would write down the 5 rotational kinematic variables. We list the values of the 3 that we know, and we also identify the one that we're looking for. We always need 3 that we know and 1 that we're looking for. Once we've identified those 4 variables, then we look at our list of variables to see which equation will help us solve this problem. In this case, it's the omega equals omega initial plus alpha t equation. If we substitute in our values, or if we do some really quick algebra here, we find that alpha will equal omega minus omega initial divided by time. Then we can enter in our values and solve for our rotational acceleration, which is 0.5 radians per second squared. So remember, it's really important that first we draw our motion map. We make our list of variables with the 3 variables whose values we know and the one we're looking for. We identify the equation that we need. We do the appropriate algebraic manipulation, and then we substitute the correct values to arrive at our answer with the correct units. Here's another example of rotational motion. Notice that this B is moving around in this circle in a clockwise direction. So remember, our first step is to draw its motion map. Let's draw the rotational velocity first. So there's our first rotational vector. Again, these are called pseudo-vectors. And then as the B goes around, we can continue to draw its vector until it gets to the 5-second mark. Accordingly, we can also draw the angular acceleration vector. In this case, it points in the opposite direction because the rotational velocity is slowing down. And we also notice that as we draw it as the same length because the angular acceleration is constant. So if we were asked the question to derive the angular displacement of the B after 5 seconds if it starts with a clockwise initial rotational speed of 1 radian per second and slows at a rate of 0.125 radians per second squared, then our first thing that we need to do is look at our rotational equations. So we've already drawn our vectors, our rotational acceleration, and our rotational velocity vectors. We make, again, a list of the 5 variables that are studied in rotational kinematics. We identify the 3 that we know. In this case, it's the initial rotational velocity, the acceleration, and the time. And we also identify the one that we're looking for. So we need to find an equation that has the rotational displacement, the initial rotational velocity, the rotational acceleration, and the time. And in looking at our 3 rotational equations, it would be this equation here. So our next step would be to enter in our values because we don't need to algebraically manipulate this equation, and then calculate our answer, which in this case is negative 3.44 radians. One thing to notice is that the speed was given to us as 1 radian per second, but we had to realize that it's clockwise. So that's why there's a negative placed in our initial rotational velocity.